Under what circumstances can you describe me as a system, quantum or otherwise, without also having to describe everything else in the universe, whether it be in this room or beyond? One obvious answer is, suppose nothing else in the rest of the universe actually affects my dynamics, so you can model me without having to model anything else. That's obvious. That's also incredibly rare. So usually there is some aspect about the world around us or the world around the system that we're considering that is affecting that system. Now in some cases it's very stable and static. For example, the gravity in this room, even though it's dependent on a large number of astronomical bodies, they're effectively not changing on any timescale I care about, so I can treat them as a very static environment, and I can just model me without having to describe that structure. But supposing I was doing something more elaborate, supposing I was causing the moon to wobble by my dynamics, then obviously the gravity in this room would be affected by my own dynamics, and so I'd have to model both systems together. So what we need really is an environment that is really boring, an environment that is not being changed by my dynamics. So if we had some system that we're trying to consider, then often the initial state of that system and the state of the environment are uncoupled. They're separable in some sense. But after some time, this system is going to be sending out some information, it's going to be interacting with that environment, and that will tend to entangle them. Now, if our environment, and the word reservoir we used a couple of times is a very suggestive one, if it's sufficiently big and of the right structure, then that information is really not going to affect the state of that environment to any significant degree. And what that means is that the reverse process, where changes wrought by the system come back to change the system in a later time, it won't happen. And if that doesn't happen, that means that the dynamics of this system are not affected by what happened in the past. And when that is the case, then what you have is a system that's called Markovian. So under those conditions, where your system is sufficiently separable from your environment and the evolution is sufficiently Markovian that you can describe an equation of motion for your reduced density matrix without having to describe your entire environment, that equation of motion is called a master equation. And it turns out there's not a lot of freedom for master equations. If you have a Markovian master equation that's time homogeneous, because it has to be trace preserving and keep the reduced density matrix as a completely positive operator, then under those conditions the master equation has to look like this, where this H is a Hamiltonian, therefore it's Hermitian. These CJs can be any set of operators, and this curly D is what's called a super operator, which is defined like this. So this thing here is a super operator because it doesn't just act on one side of rho, you can see it acts on both the left and the right of rho, but it is still linear in rho. Now looking at the master equation, we can see that these terms here are very unsurprising because if we didn't have any interaction with our environment at all, we'd expect our evolution to look exactly like that, just defined by the Hamiltonian of the system. Now if we do have some interaction with the environment and then we trace over the environment, then we get extra terms in our master equation, our equation of motion for our reduced density matrix, and they have to be of this form. Now this form, we don't have to have a particular number of these, there could be just one of these terms, or it could be up to an infinite sum of these terms. So this master equation is in what's called Lindblad form.